To motivate our next topic of kinetics, let's look at something like diamond. According to the phase diagram, all carbon at normal temperatures and pressures should be graphite. So there should be diamond spontaneously converted to graphite at normal 1 atmosphere and 25 Celsius. That reaction never basically happens. Diamonds are still essentially forever. Why is that? Well, that's the topic of chemical kinetics. In this part of the class, we're going to answer these sort of three key questions about chemical reactions. One, how fast do chemical reactions proceed and why? That's going to be the topic of kinetics. That will lead into the last two areas of the class, equilibrium and thermodynamics. Our first topic of chemical kinetics, we're going to just start with one key idea. How can we determine the rate law, which is, as we'll see, sort of a key summary of the kinetics of a chemical reaction, for a particular chemical reaction? The starting point here is that reactions are complex. We know the reactants and products, but the balanced chemical equation, like the combustion of methane here, doesn't tell us anything about the steps by which the reaction takes place. So we're going to need experiments to figure out exactly how reactions occur. In this part of the class, we'll often start or define things with a generic reaction, so something like this, which is some number A moles of A react with some number B moles of B to form some products. We don't really know what these numbers are, and in this case, it doesn't actually really affect us too much, but it's just, sort of any chemical reaction. The chemical reaction is going to depend on how much of the reactants that we have. In general, more reactants is going to lead to a faster reaction, a greater rate, but we don't know exactly how. In some cases, it would be a linear relationship, something like rate proportional to the concentration of A. Note that this notation you may or may not have seen before, but we're going to use it really consistently in this part of the class. Something like concentration of A means the moles of A per liter, right? Or the molarity of the substance A. So it's the molarity of each substance. We use the brackets to denote concentration. Other substances, it might be the case that the rate has a quadratic relationship with concentration. Or for other things, actually, the rate doesn't depend on concentration at all. We see here we've got powers here, exponents. So if we want to use an exponent to represent a case where A doesn't affect the rate, we can use a zero power, because remember, anything to the zero is equal to 1. So with that starting point, we have a general form of the rate law, where the rate of the reaction, which is going to be in units of molar per second, how fast is the concentration changing, is equal to K times A to the power of X, so the concentration of A to some unknown power X, times B to some unknown power Y, where again A and B are those concentrations of each substance, and X and Y is this new term, the orders of the reaction in A and B. The last key term to define right now is this overall order. So first, our terminology, the order for A is X, so we would say the reaction is like Xth order in A. So first order in A, or second order in B, for example. Then the overall order is just add the two up. So add up all the orders. So X plus Y is the overall order of the reaction. Again, we need experiments to get this answer. Before we show that process, let's look at an example here. So let's say we did some experiments on this reaction, CH3Br plus Cl minus goes to CH3Cl plus Br minus. We've done the experiments and we've figured out that the rate law for the reaction is that the rate of the reaction is equal to the rate constant K times the concentration of CH3Br. It's CH3Br to the first power, which is just itself, so that's why we just have CH3Br here by itself, with no exponent. What can that tell us about the reaction? So first we can think about the orders. The orders are given by this equation. So again, since there's no exponent here, remember that anything to the first power is itself. So that means the order in CH3Br is just 1. Cl minus isn't in the rate law right now, so that means that Again, if we had Cl minus there, we'd have to take it to the 0 power to get it out of the rate law. So that's just the meaning of the 0th order. Once we know that, we know the overall order of the reaction is 1 plus 0, or first order. Next, if we think about the meaning of each of these, well, if this is just rate is equal to K times CH3Br, just like when we were doing light earlier in the class, that means we have that direct or linear relationship. If I double CH3Br, the rate is going to double, since they're on opposite sides of these equation, and there's no exponents here. I can delete that now that we've defined it. That means I have that linear relationship, so this would be a direct. Now for our other reactant, Cl minus didn't show up in the rate law at all, so that's an independent relationship. The idea here is that the Cl minus concentration doesn't affect the rate. If it did, it would have to be in this equation. Next, if we move on to the meaning of those relationships for how the rate depends on CH3Br, when CH3Br triples, because there's that direct or linear relationship, the rate triples as well. When Cl minus triples, on the other hand, because the rate is independent of Cl minus or doesn't depend on it at all, the rate is unchanged. It stays exactly the same, no matter how big Cl minus is. So that's what the rate law and specifically the orders do. How can we determine those from experiment? To do this, we'll use the method of initial rates, where we'll run experiments where we measure the initial rate of the reaction, so just for the first few seconds or minutes after starting it. That'll be our dependent variable. For experiments where we're going to vary the reaction concentrations, or reactant concentrations, so it's our independent variables. Very much like a high school or middle school science project, where when we want to look at multiple variables, we need to just vary one at a time. That's exactly what we'll do as well. Here are the 3 steps for reference, but we're going to write these out as we go along. First, we'll do the rate law. Then we want to look at those trials where only one reactant concentration changes. Again, just like middle school or high school science, keep everything else constant as a control. And then last, we'll get the rate constant. This, again, sort of shows what will happen when we do that comparison, but I think it's easier to first do an example to see what's happening. Okay, so here's our example. We want to determine the rate law for the reaction, all the orders and the rate constant, its numerical value in units, for this reaction between water and CH3Cl. We did this experiment 4 different times, measuring that initial rate, and this is the data we obtained. So let's follow the steps. Number 1 is write the rate law. So the rate law for this reaction is rate. Always, that's on the left-hand side, equals, then our rate law always has a rate constant K, and now we have the reactant concentration. So H2O is the first reactant right here, and that's going to be raised to some unknown power x. Remember, we're going to have orders x and y, and then we're going to multiply that by the other reactant concentration, CH3Cl, to some unknown power y. So that's our general form of the rate law. Next, we need to do those comparisons where we look for cases where only one reactant concentration changes to determine the order in that reactant. We'll be able to do that 2 ways. First, by actually doing the math, taking the rate law for each trial, plugging in and dividing them. We'll see, though, that it's much easier if we just remember the meaning of each order. So we'll sort of show both of those, but overall we'll lean on this easier method, I think, just because it's less math and faster and more intuitive. Okay, so first we need to find those trials where only one reactant concentrations changes. So if we're comparing our trials 1 and 2, CH3Cl stays constant, but H2O changes. If I'm looking at those, I would say it goes from 0.01 to 0.02, so H2O doubles. That's the change. So this is the starting point for our sort of easier way of doing this, but let's do it one time by plugging in. So if we plug in, we can say that like the rate in experiment 2 is equal to K times the concentration of H2O is 0.02 to some unknown power x times the concentration of CH3Cl, which is 0.03, to some unknown power y. These do technically have units on them. And then I can say the rate in trial 1 is equal to, again, k times 0.01 to the x, I'll get my molar back in there, times 0.03 to the y. So these are the two reactions or trials we're comparing. What we do then is divide those two trials. So when we divide those two trials, it really simplifies what's happening here. So the reason we only want one variable to change it at a time is that makes everything else cancel. So all this stuff is constant, or is the same on top and bottom, so it cancels, and the k's cancel as well. Then we do need to be able to sort of use this exponent fact that if I have, say, like a to the x over b to the x, that's just equal to a over b, the whole thing, to the x power. So we can simplify this to say rate 2 over rate 1, and I'll plug those in. Those are 14.4 times 10 to the minus 4 over 3.6 times 10 to the minus 4 is equal to, again, the concentration of 2 over 1, so this is 0.02 over 0.01, all to the power of x. When I simplify that, I get 4 on the left-hand side, because when I do this division, this works out to just 4, is equal to 2 to the power of x. And then the question is, what exponent there solves the equation? The normal case we're going to work with in class is where those exponents are 0, 1, or 2. So if you think about which of those numbers solves the equation, it's 2. Because 2 squared is equal to 4. So that's sort of the mathematical approach. You don't have to do this division every time. The reason we keep the other one constant is because all that stuff always divides out. And what we can just do is look, how does the concentration affect the rate? So if we do this 2x in H2O, if we can identify or just do that division, rate 2 over rate 1, 14.4 over 3.6 is equal to 4x, then we can simplify that and sort of directly get to the comparison we want to make. Doubling the concentration caused the rate to go up by a factor of 4. That's a second order or squared relationship because these didn't go up by the exact same factor. That would be first order. This went up by 2 squared. So again, you can sort of skip right to this. If I just highlight which number is where in this equation, that factor of 4, that's that sort of rate. The shorthand I would use to represent this is that we have sort of like the rate factor. That's taking the ratio of the rates there, is equal to the concentration factor to the order. Before we do the next comparison, let's look at exactly how that works. So let's look at if we have different concentration factors, how is that going to affect the rate? So again, these columns here are if order is. So if the order happens to be 0th order, how does doubling the concentration affect the rate? If it's first order and second order and so forth. So if it's 0th order, remember that that's the case where the rate is independent of the concentration. So in this case, the rate factor, so these boxes here are sort of what rate factor we would get if the order is each of those things. So here we would get 1x, or we could view that as unchanged. If we triple the concentration, again, it doesn't matter. It will be 1x or unchanged. Now, if it's a first order reaction, that's that linear relationship. So in that case, doubling the concentration is going to cause the rate to double. So again, I'll just summarize that as 2x. Again, if I triple the concentration, the rate's going to triple. If the order is second, now that's that squared relationship. So the rate goes up not just by a factor of 2, but it goes up by a factor of 2 squared, or 4. So 2 squared is equal to 4x. If we triple the concentration, the rate will go up by a factor of 3 squared is equal to 9x. So with that table, we can see that most of the time we can really just do this by eye. We don't need to do a lot of calculations to get the orders. The orders just tell us what type of relationship we're dealing with. Again, to do the order in H2O again, doubling H2O caused the rate to go up by a factor of 4. That's that second order relationship. And that's what we found in that first trial, was that x from that first comparison, that x was equal to 2. Now let's do that for the other reactant. We have to also figure out CH3Cl. In this case, the only two trials here that work are, I'm trying to find them, we have to compare trial 2 to trial 4. For that comparison, H2O stays the same, but CH3Cl doubles. So again, I always like to compare sort of like small to big, or I'm taking like big over small. So this is a doubling of concentration. What happened to the rate? In this case, you probably can see it. I mean, you can do the division, 28.7 over 14.4, but hopefully you can see that, yeah, 14.4 times 2 is like 14 doubled is 28. That is actually about 28.8. So this is a doubling of the rate. So in this case, doubling the concentration caused the rate to double. That puts us right here, where it's a linear relationship. We changed the concentration, the rate changed by that exact same factor. So from that comparison, we know that y is equal to 1. Again, to show that in a little bit more math, again, we could say that the rate factor is equal to that concentration factor to the y. So 2 is equal to 2 to the y, and y is equal to 1, right? The only way we can get 2 to some power to stay equal to 2 is if y is equal to 1. So this is definitely where just remembering some of those exponents and their rules comes in. At this point now, we have that it's second order in second order in H2O, first order in CH3Cl. The overall order is 2 plus 1 is equal to 3, just adding up the orders in each reactant. Now that we know x and we know y, the only thing that's left unknown is k, and we'll be able to solve it by using the data from any one of these 4 trials. A good check on your overall answer is that, again, it's called the rate constant for a reason. It should stay constant. So if you plug in data for any of these trials, you should get the exact same answer for k. A good idea to do when you're checking on a quiz or exam. Now, first step is solving. So I'm going to plug in my x and y rate is equal to k times H2O squared times CH3Cl, because again, x was equal to 2, so that goes in, and y was equal to 1, so that's CH3Cl to the 1. Again, remember, anything to the first power is just itself, so we can safely drop that to the first power. Now we solve for k. We have a bunch of stuff on the right-hand side. We just need to move it all over to the left-hand side. So divide both sides by H2O squared to cancel that, and CH3Cl. So a little bit more algebra here than on exam 1. Definitely that's a trend on exam 2. But again, if you keep practicing it, you should definitely be able to do it. Now, again, if I just double check everything, H2O squared canceled, CH3Cl canceled. I have rate over H2O squared times what did I do? HCl, sorry. I got that way off. CH3 CH3Cl is that concentration, is equal to K. And then I can just start plugging that in. So I can pick one trial. Maybe arbitrarily I'll pick trial 1. It's the first one. So I plug in all these things from trial 1. So I'll use the rate from trial 1, which is this number up there. 3.6 times 10 to the minus 4 molar per second, divided by, now I'll take H2O. In trial 1, that's 0.01, so 0.01 molar squared, times, now I go to CH3Cl, 0.03. Remember here in your calculator that this stuff all needs to be in the denominator, so you need to either find a way on your calculator to make it look like a fraction like this, which some calculators can do, or use parentheses here. So you can, if you type it in as 3.6 e minus 4 divided by open parenthesis 0.01 caret 2 times 0.03 close parenthesis, that will in fact work. And when you do that, you should get 120 as the number that comes out. Now the units do all work out if we just try to cancel them. So molar cancels here. Now this is molar inside of that square, so just like the number gets squared, the unit gets squared too. So that's going to come out as a molar squared on the bottom. We also have a 1 over seconds on the top, so that's also on the bottom. So both of those end up on the bottom, and we get 1 over molar squared times seconds as my units of the rate constant. I'm not going to do it now, but again, a really good check would be to either plug in another value and solve for K, or right, the other way you could do that is, now that I know K, just type out this equation and check that for trial 2 I get the correct rate. Either way would work to sort of double check that everything is working properly here. So that is the entire process. Notice that when we do that, naturally we get the units of K that come out from doing that calculation at the end, based on basically how many molars end up in the denominator there. It turns out that just a fact of how that works is that if it's a 0th order overall reaction, the units of K are molar per second, and every time the order goes up, we get more and more molars in the denominator. So it goes from a molar on top to no molars to molar to the minus 1 to the molar to the minus 2. At this point, not something you need to memorize, but just something to notice is that the units on K line up exactly with the order of the reaction. Okay, so one more thing to show, because it could be useful in lab, is that just like when we went back and started here, dividing the two trials, that is always a valid approach to do that division of the two trials. We divide the two trials. As long as one thing is held constant, one of these will cancel out, and we'll get this equation here, which I sort of summarize as rate factor is equal to concentration factor to the order. You can solve that explicitly, though. The trick there to remember is that if I need to get something out of the exponent, I need to take ln of both sides, or really any log. I could take a normal log base 10 as well. Both of those will pull the x out of the exponent and turn it into just normal multiplication out here. So I take the ln of both sides and then divide. Now that this is an ln, this is just a number, this is just a number, divide those two ln's to solve for x. It's not pretty. I wouldn't recommend doing it very often, but it is useful. Again, you can see how that works at that rate factor is equal to concentration factor to the x. Take ln of both sides, and that gets you, again, I would just do it right here. Just do ln of 4 is equal to x ln of 2. Solve for x, and there you go. Could be useful in lab, or you might just be able to do it with the normal approach, seeing what doubles as well. So it turns out that in a more complicated situation, there is rates that don't happen to be exact integers. For our purposes, though, in class and typically in lab, we do have integer orders. Okay, the final thing I have are some examples, so determining the rate law and calculating the rate constant for a different reaction from the data. So take a few minutes to try to apply those rules, try to do all those comparisons, and then I'll show the solution. Okay, so here's our example. Let's take a look. Our first case here is that we have the rate law, so rate is equal to K. The first reactant is S2O8, 2 minus. The second reactant is I minus. And again, those go to their exponents, their orders. So S2O8, 2 minus to the X, I minus to the Y. Next, we need to do those comparisons to find the orders. So if I look, comparing trial 1 to 2 is a good comparison to figure out the order in I minus. So if I do this, I can see that I minus doubles, going from trial 2 to trial 1. How did that affect the rate? Well, it turns out that the rate doubled as well. That's something you should be able to recognize is a linear or direct relationship. I minus up caused the rate to go up by that same factor. So from that comparison, again, it's important that S2O8 was held constant, otherwise we couldn't infer that the change in rate was caused by the change in I minus, but because it was, we can actually just go right away to say Y is equal to 1. It's that linear relationship between concentration of I minus and the rate. If you want an equation, it would be sort of 2 to the Y is equal to 2. Let's do our next comparison. So now that we've got the order in I minus, we've got to figure out the order in S2O8, 2 minus. So for that comparison, let's take a look. 0.08 to 0.16, and I minus is constant, so that's going to be a good comparison. In that case, S2O8 doubles, and what happened to the rate? It happened to double again. So that means, again, they're both going up by the same factor. That's that first order or linear relationship. We can just see it sort of leaping out at us from the data. The overall order would be just 1 plus 1 is equal to 2. So that's those comparison steps. We didn't really have to do a lot of math there. It's just seeing how one thing affects the other. For 3, now we need to plug in and solve for K. When we do that, rate is equal to K, S2O8, 2 minus to the first power times I minus to the first power. Those first powers are just, themselves, so those first powers can go away. Now we can divide both sides by all this stuff, S2O8, 2 minus times I minus. All that stuff cancels, and we get a nice result. Now we can plug in and use the data from one trial here. So if I use trial 1, I'm going to say the rate from trial 1 was 2.2 times 10 to the minus 4 molar per second over S2O8 in trial 1 was 0.08 molar. And in I minus, I had 0.034 molar in trial 1. Again, make sure to keep both of those things in the denominator when you do your division. The number here works out to 0.081, and if we look at the units now, we have molar per second on top. That's going to cancel one of our molars, and we have 1 molar left on the bottom, and we always have that seconds on the bottom. So 0.081 molar times seconds. Always remember to keep track of those units when you get to these on quizzes and exams. Again, there is algebra, so there's always the possibility of making a mistake. Again, you can go back in and plug in, try trial 2 or trial 3 and see if you can get the right answer. So this shows that sort of checking your answer step, which is really useful on quizzes and exams. I'm just going to plug back into the normal rate law, K times S2O8 2 minus, just to the first power, times I minus to the first power, and I'll just pick trial 2 arbitrarily. Maybe it would have been better if I picked trial 3, because then both of the things changed from trial 1, but whatever. So I plug in K, I plug in S2O8 from trial 2, I plug in I minus from trial 2, and I see what I get. I get the rate 2 is equal to 1.1 times 10 to the minus 4. That does match what I measured, so that checks that, again, at least as far as what changed here, that's just a good sanity check that I didn't have any math errors. Again, you could go and do that for the other trials too, check all of them. I guess it only takes a second, but for my purposes, that's enough checking my answer here. Here's one more practice problem if you want to see what that looks like. You can take a minute to try to solve this. Okay, this is our second method of initial rate example. The first thing we need to do is write the rate law. So the rate law, again, is always rate on the left-hand side is equal to some rate constant K times, we look at each reactant. So Br2 is the first reactant, Br2 to some unknown power X, and then the other reactant, acetone, maybe I'll just write that as AC, to some unknown power Y. Number 2, we need to do those comparisons to figure out the order in each reaction. So remember, in each reactant, so the idea there is we want to look for places where only one reactant concentration changes. So in this case, maybe I'll show the full mathematical approach this time, as well as just that qualitative, what doubles, what stays the same. In this case, if I compare trials 1 and 2, that will be a good way to figure out the order in acetone, because Br2 is constant, that's our control. Acetone doubles, so if I go from 2 to 1, acetone doubles. And the rate, I can see that looks like it's probably just going to about double. But again, if you can't, let's show what the math looks like there, just to help people out. So again, just showing what my comparison looks like. I'm going to compare 2 to 1. So 2 is the lower concentration. That looks like it's doubling, 0.125 to 0.25. Let's see what that looks like. So the higher concentration is 1, so I'm going to write that first. Rate 1 is equal to K times the concentration of Br2 in trial 1 to some unknown power X times the concentration of acetone to some unknown power Y in trial 1. And then on the bottom, I'm going to put rate 2 is equal to K Br2 in trial 2 to the X times AC in trial 2 to some unknown power Y. Remember, the idea here is we can divide these two equations. That's a valid operation, and what happens then is everything that stays constant, all of our controls, get canceled out. So K cancels, and Br2, again, since if I look at the numbers there, it's 0.01 on top in trial 1 and 0.01 on the bottom in trial 2. Both of those things will cancel out. What I'm left with then is, again, the same idea we've been talking about, that it's the rate factor. So this over here on the left is our sort of our rate factor. Rate 1 over rate 2 is equal to AC1 over AC2 to the power Y. So again, just to show what that looks like, on the left-hand side there, I'm going to take the rate in trial 1. The rate is, again, in that rate column, so 2.86 times 10 to the minus 6 molar per second over 1.41 times 10 to the minus 6 molar per second is equal to, all this stuff dropped out, and remember when we have these two things that both have a y in the exponent, we can move the exponent outside of the division. So I'm going to do all that stuff in the middle to the y. So I'm going to take the concentration of AC in trial 1, that's 0.25 molar over 0.125 molar to the y. Now again, what I'm going to expect here is when I simplify that here, maybe I'll just make that a little bit smaller so we can get one more line of math here. This here looks like it's 2. I'll show exactly what that is. On the right hand side, when I do the math here, this is actually exactly 2. So this is 2 to the y is equal to, on the left hand side, 2.03. Again, given that, the best way to make this equation work is y is equal to basically 1 is going to be correct. Maybe there's a little bit of rounding error, but y equals 1 is going to work, because 2 to the 1 is equal to 2. So that lets us know that y is equal to 1. Again, in general, I would say you don't have to do this. If you like doing it, right, if you like doing that division, definitely do it, right? And again, sometimes it's easier to use the division to see what like the rate factor is equal to here, what rate 1 over rate 2 is, just to actually divide. But again, you can also just sort of look at this and see, oh, look, the rate went from 1.4 to 2.8 with the same exponent here, so that did actually double. So again, we can actually have seen that more directly by seeing, okay, doubling the concentration of acetone, holding the other reactant concentration constant, caused the rate to double. That's a first order or linear relationship where doubling the independent variable causes the dependent variable to double. Okay, our next comparison then is we need to do a comparison to figure out the order in BR2. For that one here, I'm not going to show the full math for that one. Again, in this case, we'll see why here. Okay, so here, trials 1 to 3 will work. In this case, BR2 doubles. What was the effect on the rate? The rate, if I look at this, it didn't change. It was a factor of 1x. It's the exact same rate here. So if doubling the reactant or changing the reactant, increasing the reactant in any way, doesn't cause the rate to change, the meaning of that is a 0th order relationship. I can also see that by using my sort of rate equation. I can see that, like, what I would get here is that rate 3, again, I always like to compare the bigger concentration on top, so I have comparisons that are greater than 1. That's going to be equal to the BR2 in trial 3 over the BR2 in trial 1 to some unknown power x. Again, when I plug in, the rate is just equal, since the rates are the same, when I divide them, that is just exactly 1. And then on the right-hand side there, again, 0.02 over 0.01, that's a doubling, or a factor of 2x. So 2 to the power of x is equal to 1. The value of x that solves that equation is, as we said earlier, 0th order. X equals 0, the meaning of that really helps you understand it. It is independent. It means that, in this case, BR2 doesn't affect the rate of this reaction at all. That's very important information about the reaction. Now we're on to our last step, step 3, solving for the rate constant K. Again, remember the meaning that K is that rate constant, the variable. So we can plug in rate is equal to K. Now BR2 there is BR2 to the 0th order, and then acetone to the 1st order. Remember our logarithm rules. Anything to the 0th order is just 1. So this whole term will completely drop out. This whole term just turns into a 1. And anything to the 1st power is just itself. So that term will also simplify. And our overall rate law is just rate is equal to K. BR2 is just 1, so we can drop that out, times AC. Now, according to the next step here, is we need to solve for K, because that's what we're trying to find. I'll go back to black. Divide both sides by the concentration of acetone. And again, now I can plug in. I'll use trial 1, say, rate 1 over the concentration of acetone in trial 1 is equal to K is equal to 2.86 times 10 to the minus 6 molar per second divided by 0.25 molar. Again, keeping track of units, since the order of the reaction determines the units here, molar will cancel. And my units are just 1 over second. And the value is 1.1 times 10 to the negative 5th. So that's the full solution here. Again, on a quiz or exam, you could check by plugging in other trials, but that's sort of the process. Once you get the hang of it, this should be a process that you can reliably carry out on the quiz, in lab, and on the exam.